About a year ago, I told you about the $100,000 GCP prize from the Google Bug Bounty program awarded for the best vulnerability found in the Google Cloud Platform. Now, a year later, it's time again, and the prize was higher too, $133,337. In this video, I will tell you the story and technical details of a new amazing winning bug. It's basically a server-side request forgery attack, but with the impact of a remote code execution inside of Google. So, let's meet this year's winner from Uruguay.
So, my name is Ezequiel Pereira.
This is him on our call when we talked about his bug, but at the time, he didn't know that he won the $133,000 yet. I pretended to just be curious about his blog post. This sounds really insane, and I was wondering if you would be interested in making a video together. He said yes, and so he started explaining his bug.
They classified it as RCE because an attacker could potentially execute code by calling some internal Google endpoints. And those internal Google endpoints, seeing that the request comes from the Cloud Deployment Manager, might allow an attacker to do actions that an external user shouldn't be allowed to perform. So it is equivalent to RCE. I never got to the point of actually executing code on Google, especially because they cut me off because they were treating this as an incident.
So his bug allowed him to basically perform arbitrary requests inside of the trusted Google network, and he could potentially reach critical endpoints. We will soon talk about this internal network because it's really fascinating. This bug combines so much knowledge about Google internals. But as he said, he never got so far to exploit it further. Google knows what impact this special server-side request forgery has and classified it as a critical remote code execution.
If you get into the internal network and are able to issue requests, it's like RCE.
It's not true in any Google SSRF case, because internally in Google, requests between services have to be authenticated. But in this case, the source of the request was authenticated with apparently high privileges. Thus, in this case, being able to issue requests is like RCE. That's why they also treated it as an incident. This is a bug that needs to be investigated because maybe somebody else, an actual attacker, used this. Of course, Ezequiel also got awarded the regular bounty program award when he reported it. So, how much was it?
You have a rewards table, and you can see that they always pay $31,000 for RCE issues in their main Google products.
What Ezequiel didn't know was that I had the Google VRP team on standby to join the call at any moment.
Yeah, I can see that.
I acted surprised why somebody would want to join the call. I accepted them all.
We concluded that you won the top prize, which is 133. So yeah, we wanted to surprise you in person.
Okay.
Woohoo!
Thank you very much.
Congratulations.
Yeah, I didn't really expect to win. I thought maybe the Firebase bug that sent tons of notifications would win.
So I guess Ezequiel needs to update his blog post with the facts. It's not just $31,000, it's a total of $164,674. Damn. But now you're ready to hear the story about this bug. First of all, there are so many Google Cloud Platform products, and as a bug hunter, you might get overwhelmed not knowing which target to pick. So, I'm curious, how did he end up researching this particular area?
Google Cloud is huge. I can assure you that I haven't even touched 70% of it. 70% of Google Cloud is completely unknown for me. I'm no Google Cloud expert. I just go through the documentation, and if I kind of understand something, then I begin looking into it. I've researched App Engine a lot because it's easy to use, easy to understand, and it is really interesting.
App Engine is one of the big main products of Google Cloud. Basically, it allows you to host web applications.
So while looking at App Engine flexible environment, I stumbled upon Deployment Manager. So here, for instance, I deploy something on App Engine flexible environment, and you can see calls to the Deployment Manager API. Yeah, and you can see like the user is guy API pro.google.com service account. Well, I decided to look into it because if it was being used by App Engine, it would probably be used by other GCP products. And when something is used internally at Google, even if it is a public product by like Deployment Manager, they sometimes hide internal settings, internal stuff that if they are not well protected, they could be exploited by an attacker. And that's what happened here.
So the Google Cloud Deployment Manager is one of those many products that he didn't know, but then saw in the logs that App Engine uses it internally to manage the servers. And I think it's very clever how he thinks about Google products that they also use internally.
For instance, I think every or almost every with google.com website is really an App Engine application. And sometimes you can see that the website is integrated with the other Google services. So you begin to wonder if it is running on App Engine, how is it connected to internal Google stuff? Or for instance, they use GCE, Compute Engine, a lot too. So yeah, and while using them, sometimes they need to do internal stuff. So sometimes they build into the public tool internal stuff that they just hide somehow from the public because they are only meant for internal users. If you pay attention, sometimes the documentation also references internal stuff and you say, what does this mean in the documentation? And it doesn't make sense because, well, it is intended only for Googlers.
I think this is a very valuable tip for aspiring Google bug hunters and probably the most important takeaway of this video. Approaching the target with the mindset that if a product is also used internally by Google, maybe there are undocumented internal features exposed that could be exploited. And he saw that the deployment manager was used by App Engine, so he decided to hunt for bugs there.
So I knew nothing about deployment manager. I didn't understand what it was for. Even right now, I'm not pretty sure why it exists or how is it useful for a developer. But yeah, I had to read the deployment manager documentation like 4 or 5 times until I kind of got the idea of what it was for.
Let me try to give you a brief summary of what the deployment manager is. It all starts with a configuration or template describing some resource. Here, for example, a compute instance, so a basic server, being deployed in a US data center. It also has a hard drive attached with a Debian image on it, and it also has an external network interface with external NAT. So this is a whole machine description. Now you can take that and send this to the deployment manager, and it will then set up this server for you. So you can kind of imagine this like a Docker Compose file or maybe a Kubernetes deployment object. This is just a Google Cloud Deployment Manager config. Now let's think about App Engine, which is used to host web applications. When you deploy an app, it seems like that App Engine uses the deployment manager to describe the server where the app will be running.
I began playing like creating my own templates and creating resources and looking how it worked, looking at the different features. For instance, you know there are 2 public versions of Deployment Manager. You have the V2 version and the V2 beta version. So I looked at the differences between those 2 versions.
And one of those differences are type providers. It's a very confusing name, but it's important to understand. So, in a deployment manager config file, you have a type field, and that describes what kind of resource or server you want. In this case, it's a compute v1 instance, but that's something Google Cloud specific. What if your company uses, besides Google Cloud, also your own data center with machines you want to manage too? Type providers can be used for that. A type provider exposes all of the resources of a third-party API to a deployment manager that you can use in your configurations. These types must be directly served by a RESTful API that supports create, read, update, and delete, CRUD. So as long as you can provide a simple HTTP REST API for your data center that implements create a server or delete a server, then you can define a type provider describing your API, and then you can use deployment manager referencing your own type to talk to the data center's API. This way you can manage all your cloud resources in one place. Anyway, here is an example API request to create your own type provider with the v2 beta version. And most important is here the descriptor URL. It points to a JSON file, and this JSON file is like a Swagger API definition. This is what actually describes your API endpoints where you implement your create or delete resources stuff. The options field is also interesting. You can see here that it defines an authorization header. It's obviously important that when you implement your own API to manage your servers, that the API has some form of authentication. And in this example, you send a Google OAuth token along that you can then check. But now let's send this request.
Okay, so you can see the operation was completed. So the type provider was created. And if I go to my server, I can see that this IP connected to my HTTP server and retrieved the descriptor document for my fake API. And it provided the access token I told it should provide.
And now you can maybe already see where this is going. The bug Ezekiel found is a server-side request forgery attack. And here we control a URL that the deployment manager sends a request to. So is it as simple as, for example, pointing this at localhost or some other internal IPs or host names?
If I try to create a type provider that talks to an internal server, like server-side request forgery, it will try at first to create the type provider, but it will fail. It will say error processing request, error fetching URL localhost, error excluded IP. It won't let me do internal request just like that. I tried like setting my own domain that would like point to an internal service. You see that here it failed on the creation of the type provider. So I also tried like setting my own domain that at first points to a valid service. And once the type provider got created, I tried changing my domain to an internal server to see if maybe I could bypass it that way. It didn't work. I'm not an expert on all of this. So maybe someone looks at this, tries something, and finds a way to get SSRF through here. But I was not able to.
That would have been too easy, right? There's more to come. As a mental exercise, try to think about what you would try next, or just try to guess where this is going. This is what I do, trying to figure out if I could have found this bug too.
Then I moved on, and some days later, I decided, okay, maybe I can find an internal method used by deployment manager, because remember, Google, when using these public tools internally, sometimes they hide internal stuff inside. And sometimes they are like internal hidden methods in the API. So I know a way to list all the API methods, even undocumented ones. And it is through the metrics page here in the Cloud Console. And funnily enough, it doesn't only show the public methods, but also some internal ones if there are. So here you can see, for instance, the get operation method in the v2 version. But looking at this, I noticed that, well, you have v2 and v2 beta, but also here, for instance, here, you have dog food version and you have alpha versions, and those versions are not documented publicly. And I said, okay, I'm going to look into them.
Mind-blowing, like a detective finding small puzzle pieces. So let's see what happens when you try to send requests to those different versions. By the way, look at my face during the call. I'm in total awe right now.
I can get an operation on the v2 beta version. I can also do it on the v2 version. Let's see what happens on the alpha version. Can I call a method on the alpha version? Yes, I can. Can I call this method on the dog food version? Yes, I can. If I try a version that doesn't exist, No, it doesn't default to using a public version. It just says not found. So now I know that alpha and dog food are real versions.
And every Google bug hunter should get excited when they read dog food. Here's a Google blog about testing from 2014 describing their concept of dog fooding. Google makes heavy use of its own products. Because we use them on a daily basis, we can dog food release company-wide before launching to the public. These dog food versions often have features unavailable to the public, but may be less stable. Now, it's not necessarily a security issue that you can access a dog food version publicly, but if it's a less stable test version with maybe bugs, there's a higher chance for it to have security-relevant bugs too. So it totally makes sense to now go after this dog food version of the API and see if there are new features that are not in the public release that could be exploited.
So I began looking into the request. This method is called list types. It tells you the built-in type providers of Deployment Manager. So for instance, here at first you can see that Deployment Manager is able to manage spanner instances. I was looking into this. I scrolled here, said, okay, all of this sounds like stuff that is already documented. Until I got here. I was looking at the built-in types, and suddenly I found that with the dog food version, there's something called Google Options here. This is not documented. This is not in the public versions. So I was wondering, what is it doing here? So there I found one difference with the public API. Yeah, I looked into it and said, okay, if it is on the built-in type providers of Deployment Manager, maybe I can also see it on my own type providers.
Ezekiel maybe just found an undocumented internal Google Options field and was wondering if he can set it on his own type provider, and maybe it does something interesting.
As soon as I found this, I was really interested into it, especially because I saw this GSLB target. And I know that GSLB is the internal global service load balancer of Google. And if you read the SRE book, you can see that it might let you send requests to internal servers.
The Google SRE book he mentions is really cool. It has been on my reading list for many, many years. But I cannot read books, so I never did. Even though I haven't read it, I know it's amazing because, as Ezekiel just said, you can learn about some cool internal Google stuff. And in this case, the Global Service Load Balancer, GSLB, is important. In the chapter about the production environment at Google, you can read: our Global Software Load Balancer, GSLB, performs load balancing on 3 levels: front-end services and internal remote procedure calls. The front end handles our typical DNS queries for domains like google.com, but internally, Google uses their own system. Service owners, so basically developers, specify a symbolic name for a service, a list of BNS addresses of servers. GSLB then directs traffic to the BNS addresses. So internally, Google uses BNS addresses to identify servers. Further down, we get an example of how an HTTP request to a Google service is handled. First, the user points their browser to shakespeare.google.com. To obtain the corresponding IP address, the user's device resolves the address with its DNS server. This request ultimately ends up at Google's DNS server, which talks internally to GSLB. As GSLB keeps track of traffic load among front-end servers across regions, it picks which server IP address to send to this user. The browser connects to the HTTP server on this IP. This server, named the Google Frontend or GFE, is a reverse proxy that terminates the TCP connection. The GFE looks up which service is required, web search, map, or in this case, Shakespeare. Again, using GSLB, the server finds an available Shakespeare frontend server and sends that server an RPC containing the HTTP request. The frontend server contacts GSLB to obtain the BNS address of a suitable and unloaded backend server. So as you can see, the global software load balancer is inside the Google network. That means if you somehow can send requests to a service with their BNS address, you are really deep inside of Google, and you might be able to send really critical requests to very important internal servers. And now coming back, here you have a GSLB target field, which sounds like you can maybe specify a BNS address. Those addresses are not necessarily secret, but they are also not really public, though sometimes they leak out. You can find some of them appear in logs or API responses, but Ezekiel also had this funny story to share.
There's this screenshot that I wanted to show you. This screenshot is from a website, an internal Google website, not internal. It was a web page that was exposed publicly by mistake until yesterday. Yesterday they blocked access to it. But here you can see that you have a GSLB addresses. So this is an example of how someone might find GSLB addresses just by luck.
So fascinating, right? All those puzzle pieces slowly coming together. And we are slowly getting to the vulnerability. So we just found this GSLB target value, and there's this idea. Maybe the domain you specified here is overwritten by the GSLB target, and you can use this request from the deployment manager to send requests internally.
So for instance, here I'm trying to reach the corporate issue tracker API. So this is the symbolic name for the issue tracker API. The issue tracker API is issuetracker.corp.googleapis.com. So usually you don't have access to that. Okay, I'll try specifying this on the GSLB target. So these values, I set this to true and this to false just because through trial and error I saw those values worked. So I still set them to that. And transport, again, I saw harpoon being a transport value. So I couldn't get SSRF this way because, as you can see, my server got hit by the deployment manager request, but my server is not inside GSLB. So the request did not go through the internal load balancer. So I didn't get SSRF.
Good idea, but it didn't work. Would you have given up at this point? I might have. But Ezekiel had another idea.
I suspect it has to be with transport here because, well, it doesn't make sense for the other values to have anything with going through GSLB or not. But I didn't know what values should I put this. Should I put internal? I tried brute forcing it, but I just didn't get it right.
Okay, maybe Ezekiel just has to find the correct transport method, and then the deployment manager will honor the GSLB target address and send a request to this internal service. The problem is, this is an enum field, so you need to exactly know the name of the correct transport. That's why he tried to brute force it.
But at the time I didn't know what value would it be, and I tried brute forcing it like internal or corp or whatever, and I couldn't get it working. I couldn't get SSRF. It would always hit my own server and not the internal Google server that I wanted. And once you know what value goes there, it's really obvious. But at the time it wasn't obvious for me, so I went through, I spent weeks stuck here, and one day I finally got an idea. I wanted to use protocol buffers.
Wait for it, this is so smart. Protocol buffers, or protobuf, is a binary serialization format for data. It's like JSON, just not readable by humans. It's binary data. JSON is what normal people on the internet use, and protobuf is like what cool people use. And it's from Google. Thus, tons of Google services use, or at least support, protobuf instead of JSON. Or to be more precise, many Google APIs do not only support your basic, boring, boomer HTTP 1.1 with your neat, easily readable HTTP headers, but they also support gRPC, which is a protocol using protobuf over HTTP 2. And HTTP 2 is also binary. I wonder how many of you have actually heard or worked with HTTP 2 before?
So if you know protocol buffers, they are a serialization format that Google uses a lot. And in that format, enumerations are encoded to binary as numbers instead of strings. So for instance, here, instead of specifying Harpoon or OAuth or Google, I will just have to specify their enumeration number.
This is so clever. In your human-readable JSON, you would have to know exactly the name of the enum. But in binary protocol buffers, data is tightly packed. And for an enum with just a few options, you don't want to waste space and store long strings. Because protocol buffers definitions are compiled and shared between client and server, you can just encode it as numbers. And then you wouldn't have to know the exact name for the transport. You can just try out all of them. And so Ezekiel tried to interact with this API via gRPC. Or actually, he tried to use a trick to more easily work with it. Google sometimes supports protobuf over HTTP 1 instead of HTTP 2.
One way of looking at that is, like, for instance, specifying alt parameter here, saying I want proto, but it says proto over HTTP is not allowed for this service, in this case, deployment manager. So here Google disallows this proto fallback. So I cannot use protocol buffers on deployment manager. Or that's what I thought at first. Another thing Google has is that their staging environments are very often accessible. So I said, okay, if I cannot use proto over HTTP on the production environment of deployment manager, can I somehow maybe access their staging environment? Through experience, again, I know that in some APIs, to access the staging environment, you just need to prepend staging in the version name. Just like that. Okay, I did this. I called the staging environment and it worked. I invoked a method on the staging environment. It says my type provider does not exist because, of course, it exists on production, not on staging. So let's create it on staging.
Oh my gosh, he found another hidden version.
So here, look. In the staging environment of deployment manager, I am able to use proto over HTTP. And, well, this is binary. I don't understand. There's another way to get a protocol buffer response, which is through the content type. Content type, application, x protobuf. And again, the same.
But wait, it gets more crazy.
Something also that I wanted to mention is that Google APIs don't only serve from googleapis.com, they sometimes also serve from client6.google.com. But if you try to get a protocol buffer response from google.com, it will freak out because it says request and save for trusted domain. I mention this because the way Google bypasses this when they need to use client6.google.com is through a header that is called xgog encode response if executable, and the only value I know is base 64. So I run this and I have the response in protocol buffers encoded in base 64. If you don't have like the protocol buffer definition of a protocol buffer message, luckily the protocol buffers compiler tool, Protoc, has an option to decode the raw message and it will just give you the field number. And here I have the protocol buffer message decoded. And instead of the field names, I have like their field numbers here.
So what you can do now is craft a create type provider gRPC request with this protobuf encoding and changing the numbers to the different transport values you want to try. And once created, you can then use the JSON API to list all type providers and get the actual JSON name of it. In this way, he figured out the transport name has to be set to GSLB. Who would have guessed? And so now he created a type provider targeting the internal corporate issue tracker, specifically the REST API discovery endpoint, just to prove that he can reach it.
So there's a method in deployment manager to list the types a specific type provider handles, and it says, okay, this is what the issue tracker has. And this is live. The deployment manager right now sent a request to the issue tracker API through GSLB and got its discovery document and processed it, and it's showing us the results of what it found. This is the bug. I am able to create type providers that talk to internal endpoints through GSLB. In this case, an internal API, but it could be any endpoint.
Wow. Of course, Google has fixed this bug now, but this is such an amazing bug to me because it involved so many small puzzle pieces, so many small tricks that have to come together. I learned a lot about Google internals from this, and hopefully it can help future bug hunters too. Ezekiel, congratulations again for winning. You really deserved it. But of course, there were more cool submissions for the GCP prize. So go head over to the blog about this year's winners and learn more about the other amazing bug hunters and their findings.